Consider a hanging weight system pictured here. We have a weight of mass m hanging from a rod that is rigidly connected at its other end. In this example, let's also neglect the weight of the rod and let's assume that the system is in static equilibrium. If we take a closer look at the center portion of that rod and cut it away and remove it from the system, we will recall from statics that we have to apply forces at either end to maintain equilibrium. And in this case, we also know that the force is equal to the mass of the weight times the acceleration due to gravity. But what else do we know about this force F? We know that it has the units of newtons. We also know that it's a vector quantity with both a magnitude and a direction. We know that it acts at an infinitesimal point, and the force, as all forces, is a resultant of an interaction. In this particular case, the interaction is between the acceleration due to gravity and the mass in the weight. The force is also a resultant of another interaction, and that is what is actually happening on that cross-sectional surface. We know that it is physically impossible for us to have a force acting at an infinitesimal point. In reality, that force will be distributed over that cross-sectional area. We will call this distributed force stress and denote it by the Greek letter sigma. We also know that if we integrate that stress over that cross-sectional area, we get exactly the resultant force. So what else do we know about this new concept of stress? Well, it has the units of force per unit area, because if we integrate it over an area, we will get force. It also is a vector quantity because it has both a magnitude and a direction associated with it, and it acts at an infinitesimal point, just like force. And what it actually represents is the intensity of a resultant force at a particular point. Looking at stress in this manner, and looking at the units of stress, you might ask yourself, is stress just simply force divided by area? Well, not exactly. Stress is actually the intensity of a force. And although force divided by area might actually be a nice approximation of what the stress distribution is in an actual case, stress is actually the limit of force divided by area as that area approaches zero. And the reason this is important is there may be some cases where you have higher stresses acting on a surface and in other areas lower, as shown on the right here. You could have a distributed level of stress. And this is important in materials, the performance of the materials, and in the failure of materials, where the average stress shown on the left might actually get you into trouble. It was mentioned earlier that stress is a vector, and we know that vectors can be broken down into components. So let's examine this concept in detail. Take the generalized body shown here in blue, subjected to several forces, F1, F2, F3, and F4. If we take a cross-section through this body, we know that there has to be some sort of stress distribution acting on the cross-sectional area to maintain equilibrium. If we now look at a small area, delta A, of this surface, we know that there is a small resultant, delta F, acting on that area. If we zoom in on that and apply a coordinate system to that surface where Z is normal to the surface and X and Y are parallel to the surface, we can see that the resultant force, delta F, can be broken down into a normal component, delta Fz, and two components parallel to the surface, delta Fx and delta Fy. These, however, are force components, not stress components. We can, however, convert them into stresses as we did before. If we look perpendicular to the surface, we can define a normal stress. And that normal stress is the limit of the resultant component of force, delta Fz, divided by the area, delta A, in the limit as delta A approaches zero. We will call this stress sigma zz. The first subscript in this labeling refers to the outward surface normal direction. So the normal vector for our surface delta A points in the z direction. The second subscript refers to the resultant force direction. So delta Fz is also in the z direction. Now for a normal stress, the resultant force direction and the outward surface normal direction will always be the same. So we often write this as just sigma z. Parallel to the surface, we get two stress components, and we will call these shear stresses. The first one we will denote by the Greek letter tau, and it is the resultant shear stress in the x direction. So that is the limit of delta Fx divided by delta A as delta A approaches zero. We use the same subscript notation here, so the first subscript, Z, refers to the outward surface normal direction, and the second subscript refers to the resultant force direction, which is in the x direction. Similarly, we get a second shear stress component that the resultant acts in the y direction. We call this tau zy, and it's the limit of delta Fy over delta A as delta A approaches 0. Let's now look at the general state of stress in 3 dimensions. We just looked at decomposing the resultant force delta F into 3 stress components, sigma z, tau zx, and tau zy, on the small area delta A. If we're talking about stress at a point in a material, we have to remember that that material exists in 3 dimensions. So it is not really a small area delta A, but a small volume delta V. If we consider this cubic volume in this Cartesian coordinate space, we can then start to look at the different faces. We have the ZX plane with a normal stress sigma y and 2 additional shear stress components, tau yz and tau yx. And we also have the ZY plane with normal stress sigma x and shear stress tau xz and tau xy. And of course, we have the reaction stresses on the opposite faces, which for an infinitely small volume will be equal to their opposing face to maintain equilibrium. So we get a 3x3 matrix of normal and shear stress components as shown here to describe the general state of stress in 3 dimensions. I also want you to remember that although we're drawing this as a cube, it is infinitesimally small. It represents a point. However, in order to visualize the stress components and the direction and the face that they would be acting on, we do draw it as a cube. The stress state in many engineering problems can actually be reduced down to 2 dimensions. In such cases, our 3x3 matrix reduces to a 2x2 matrix with 2 normal stress components and 2 shear stress components as shown here. We will often draw this pictorially as shown on the right with a square of width dx and height dy with the stress components acting on it as shown. Now, as with the 3D stress state, it is important to remember that this square still represents a volume. In fact, it has a thickness, a differential or infinitesimal small thickness coming in and out of your screen. However, as we did before, even though it's drawn as a cube or a square, it still represents a point. When dealing with stress components, we have to apply a sign convention. We will be using the following sign convention throughout this course. Now consider shear stress component tau xy. We know from the subscripts that this stress acts on a surface that has a normal vector in the x direction, and the resultant force from that shear stress is acting in the y direction. To apply the sign to this stress, we will first take the magnitude of that stress. We will then multiply it by the direction of the surface normal relative to our coordinate system. So if the surface normal is in the positive x direction, we would multiply it by positive 1. We then multiply that by the sign for the resultant force direction. So if it's in the positive y direction, this would be a positive 1 value. And remember, if we're dealing with normal stresses, the single subscript can be expanded to a double subscript in order to determine the sign. Let's look at this for an example. Here we see 2 stress states that are the same in direction but opposite in sign. If we look at the stress state on the left, our outward surface normal is in the positive z direction, and our normal stress sigma z has a resultant in the positive z direction as well. So our stress becomes sigma z, magnitude of sigma z, multiplied by positive 1, multiplied by positive 1, which gives us a positive normal stress. Remember, the first positive number is the sign of the outward normal, and the second positive number is the sign of the resultant force. On the right, we have a positive outward normal direction, but our resultant is in the negative direction. So in this case, sigma z would be negative. If we apply that to the shear stress components on the left example, we see that they are all in the positive direction, while on the right, they are all in the negative direction. When dealing with stress components, we have to apply a sign convention. We will be using the